may have lost a couple of people to the firmware, firmware 103, but we'll keep going. Watch the recordings later. So yeah, once you're done your layout, then you'll be sending the board off to manufacturers. Manufacturers require a board format, a file format in Gerber. It's basically the equivalent of a PDF for a PCB design. It's a pretty old format, but they use that in all their machines. It's much easier to program a CNC machine with the Gerber than it is an Altium file. So you'll generate the Gerbers in Altium, and then it's always good to double check them with an online Gerber viewer. The manufacturers will create the boards to within the Gerber, not what's in your Altium design. So if there are any mistakes in the Gerber, and Altium is a very good program, and I don't think there are any mistakes in their output, but it's always good practice to double check. One of the things that can happen is that there are some inconsistencies in what should be manufactured. So this board here is the current sense that we sent to JLC PCB, and they had some comments for us that we wanted to see. They wanted to see like, if we actually wanted to have the solder paste open over the test points here. The IPIN are test points for ISOSPI and 5 volt and 12 volt test points. Yeah, basically wanted to see if we actually want those open in the stencil and put solder paste over them. But we do not, because they're test points, as we don't want them soldered. So they double check with us on that. And we don't want to be, we want to have them waiting on us to manufacture the board, because that's one of the biggest lead times in our design cycle. So it's good to keep an eye on your email once you send the boards out for any questions that the manufacturers will have. So when it comes to actually manufacturing the board, there's a couple different technologies that the companies will use. A super good video that is on this Strange Parts YouTube channel that did a factory tour of the JLC PCB factory. The link to that is at the bottom. I highly recommend you go watch that. It shows you what goes on behind the scenes with everything. But basically, the process is they take all of their orders from all the customers and panelize them onto larger sheets. So that means just putting all the boards together so that it makes a large board. They have a standard size that they'll use. So I think it's something like 400 by 500 millimeters. And they put all their boards on there into that size, and then we go through the whole manufacturing process as that panel. So it starts with a copper clad epoxy board. There's a couple different materials that can be used for that, with advantages and disadvantages with electrics and stuff like that. But we use just the standard for material for all of ours because it's pretty cheap. Yeah. And it goes through a series of CNC drilling, drills all the vias and holes and board outlines in that sheet. And then the vias, if you design PCBs, you know, they're pretty small. They're like 0.2 millimeters or 0.3 millimeters in diameter. And they do drill it with the drill. So it's a pretty small drill tip. And I think Nate, went to electrical guy for MS10, PM for MS10, mentioned that the drill tips are typically good for about 1,000 drills from swapped out. So if you're littering your board with vias, making via stitching all over it, give it a reasonable number. Don't put it every half centimeter. Space them out a little, and the manufacturers will be a lot happier with you. Yeah, multi-layered boards are made from they build up each layer individually and then press them together, and then they stick bias through them. So that's this is one of the cool things I didn't know. I thought it would kind of just be I don't know how I thought they did make it, but yeah, that's one of the cool things. And then for surface finishes, There's two of them that are pretty popular, HASL and ENIG, hot air solder leveling, and electroless nickel immersion gold. The hot air solder leveling is the cheapest. It works. If you're doing any high volume, high reliability stuff, ENIG is always better. It'll give you less corrosion on the surface, and gives you a better connection with the gold. The solder will like to stick to it better. The hot air solder leveling will, over time, it will corrode. There are a few extra impurities in there. But for our boards, it's not too much of an issue. But we'll likely do all of our prototypes with Hazel because it's cheaper, and hopefully move to ENIG if we can get a board sponsor for the final versions of the boards. So once you have your board in hand, then it's time to do some assembly. So that's getting all the components. They're all ordered from the suppliers. And hopefully it's just a day mouser. Get all the components in. Then it's time to put all the components on the board. So for a couple of different ways to do that, you can use a stencil and a reflow oven. So the stencil, basically a metal sheet that has openings in it for all the pads and you put solder paste on there and scrape it across, and all the solder paste ends up only on the pads where the solder, the stencil paste was open to allow the solder paste to go through. So one thing to keep in mind there is that components with really small pitch, so pins are really close to each other, can be difficult to do with that technique. Typically, there either won't be enough solder paste on there because it'll stick to itself and stick to the stencil, or there'll be too much on there, and you just squish too much through the stencil opening, and all the pins will be bridged. So typically, those can all be fixed with hand soldering and solder wick, which does take a fair bit of practice. It's not too hard once you get used to it, but it can be pretty annoying if you're working on a component for a few hours, trying to get it unbridged. There are a couple techniques that are in the link there that can help you do it a lot better. I'm just watching other people do it and then doing practice is pretty good. Pretty good strategy for that. For the stencil, once you've put all the solder paste on the board, then you can place all the components on top of it. For the industrial machines, they use what's called the pick and place machine. I think they're pretty cool. They take all the components from the tape and reels packaging. You can see them loaded in the top right picture here. There's plastic strips that are coming off the tape and reel. And then those get loaded into a pick and place machine. They have optical inspection in there to figure out the orientation of the component when it picks it up. There's vacuum pressure to pick up the component, and then they go over to the PCB. They place it on the PCB in the correct orientation, the correct spot, as you can wire your Gerber files. Your assembly files will dictate where components are placed, given a few reference designators on the board. The references for the pick and place machine are called fiducials. Basically just it's a circle on the board that says this is the 00 origin for the pick and place machine. So it lines up to those fiducials. There's typically two or three of them to correct for any skew as the board is loaded in. Yeah, so it finds the fiducials, and then it goes and finds all of the components in the tape and reels and places it. I think the machines are pretty cool to watch as well. But they do take a while to set up, and they're pretty expensive, so we don't use them. We use hand soldering, or hand placement, we just use tweezers. So it can be a tedious process. Yeah, I should say that it's quite a fun process. For large boards, I can see it's a bit tedious, but for smaller boards, it's pretty cool to see to do it all yourself. Once it gets upwards of 50 components, it gets a bit tedious. It's definitely something that we'll get to do in the hardware tutorial boards. once we're back on campus, hopefully in the fall. If it depends on how you're engaged on campus, even though school's online. But yeah, that's one of the cool things about how easy this process has become. There didn't used to be PCB manufacturers that would ship it quickly and cheaply, and component manufacturers that have all the components you want. So in the past maybe or so, it's become a lot more available to pretty much anyone who wants to make it. And then once the components are soldered, a bunch of the industrial places will use X-ray inspection and some visual inspection on the soldered joints as well. We just use a microscope and our eyes. So we can miss a few things, but the microscope is pretty good for making glitches on small pitch components. Then we go back and fix those with your solder wick and your solder iron. There's a link here to a JLC PCB factory automated assembly where this picture comes from. You can see what the high-end stuff does, and then you can get to practice with the tweezers if you want. One part that's super important that many people forget to do is cleaning your board. The solder process will leave some residues on your board from the flex that's used to clean the pins as you solder. And those residues over time, they will become corrode into your board. In this picture here, they've broken the trace. So that board would be completely toast. Looks like that board had maybe it wasn't just residue on the board. There's some other problem with that. Maybe too much current going through that trace, so heat it up. But the residue on your board can cause problems. It is slightly conductive, so it's something you can do to clean it off. No clean flex that we use does not mean you don't have to clean it. It's just low residue. The flexes that used to be used had a lot more residue in them. So when they switched to this new type, they called it no clean, but it's not actually no clean. You still have to clean it. So to do that, we use isopropyl alcohol, and there's a brand of wipes called Chemex that we use in the bay. Just a brush will get all the residue off pretty well. And one of the Ultimate podcast is they have an episode on cleaning boards, and it's super informative about why you actually clean it, and it goes a bit more in depth onto the chemical issues that actually cause the shorts between layers in the board. So definitely give that a listen. It's super interesting. So now you've got your board populated with all the components. Now you actually have to prove that your design does what you intended it to do. So I think it's always helpful to have someone else help you in validating your design, because it's super easy to get caught in the being overconfident in whatever you've made. I've definitely been trapped thinking that I've designed it, so it must work. But there's always some little error that I would never catch just because I'm overconfident in some things. It's always helpful to have a second pair of eyes on it that will call you out on these mistakes that you made. So when you're testing it, you have to prove that it works according to the requirements that we said earlier. So some of that could be fault injection, such as CAN lines shorting together, or as a signal line shortened to high voltage or ground. We don't do too much of that type of testing. Industry does do affirmative fault injection testing to make sure that under certain fault conditions, their boards will still operate properly. Something we might get into in the future, but for now, fault injection testing isn't part of our design process. We focus on requirements testing. It requires measuring voltages and signals. When you're doing measurements, you should always know what to expect before you actually take the measurement. If you don't know what to expect in doing the measurement, it actually doesn't give you much information. It just gives you a waveform on the oscilloscope, what that node looks like. It doesn't really tell you if it's operating properly if you don't know what it should look like when it's operating properly. So there's another Ultimate podcast on that. I forget which one it is. They call it rule number 9. There's a professor in the US somewhere that always teaches his students to follow that rule number 9 of always know what you're going to measure and know what to expect before you do a measurement. I'll try and find a link in there. Yeah, that's a super good rule to follow because then you actually get some good info from it. You use oscilloscopes, thermocouples, and that kind of stuff. You need test points for it. For oscilloscopes, you need to reference the probe to the ground. It shows you the voltage waveform over time, like in the top right. So one side of the probe has to be connected to the ground, the other one to your signal. And you'll get the waveforms shown there, or whatever waveform is on your board. This one is from the power distribution testing. Testing 2 different channels of the input, seeing if it would switch from the aux battery to the DC-DC properly when the DC-DC is activated. It switches from one channel to the other. Both supplies were valid. In this case, we hit a reset loop issue, so both supplies went down unvalid. The purple and teal lines there. That's, you can read about that on Confluence if you want. Yeah, so this is where those test points come in. You need to have those test points so you can validate it. Any components that you think might be getting hot, such as MOSFETs if they're driving high currents, or load switches, or resistors that are very close to their max power rating. You want to make sure they're operating properly and not heating up too much. So thermocouples are great for that. Another great tool is a thermal camera. We have, we do have a FLIR one that plugs into your phone today. So you can use that to make sure that your board isn't getting too hot. And then for simple hardware testing, to test inputs and outputs of your board, Firmware has made some amazing programs. They call them smoke tests for CAN, SPI, and S-grid-C. Sorry, just SPI and S-grid-C. CAN you can just test separately. We have a that will interface with the chips on your boards and make sure they're actually doing what they're supposed to. So you can just make regular registers in a SPI chip and make sure that it produces the right output on its pins. The S-grid-C I/O expanders, you can test those out without a full firmware implementation for your board. Super important because it verifies that the hardware was done correctly and the connections are there between the SPI and S-grid-C pins. You didn't shift them over by one pin or something like that. I have done that in the past. Where you shifted by one pin. So definitely one thing to watch out for and test to make sure that it's done properly. And then the last step when you're doing the full integration testing. This is where you bring in firmware and you bring in all the ports and loads that it connects to. So for the BMS carrier, you'd have the BMS carrier there, you'd have the aux battery powering it. You'd have the AFEs and the current sense and the battery stack, and run the firmware on it and make sure that it actually produces what you want. And hopefully, any issues found at this stage are just firmware issues and not hardware issues because you've done all our validation testing at hardware already. So yeah, when you're doing this step though, especially as firmware is developing the firmware for the board as well, it's super important to stay in contact with the firmware people that are making the program for your board, because they'll need to know what the board is expected to do, how to interact with the other boards to design their the workflow for the firmware program as well. So yeah, that is well, not the last slide, one more. That's a lot of steps in the validation and bring-up process. Large companies will have teams dedicated to pretty much each slide. above. So it's a lot of stuff to take on, but we're all here to help each other out. If you need help for documentation or how to test something, just a signal you're not sure what to expect on it, just ask. We're happy to help, especially because it makes the car better in the end. It makes us all learn. Better engineers too. So, and that is that's the end of it. So there's a whole bunch of links and images from some acronyms. There's a Vultine podcast. The first one I mentioned for cleaning the boards is there. So definitely go have a look at that. Yeah, is there any questions? He just says in the chat there's also the heat gun method for hand soldering if you have particularly a troublesome part. It's definitely not forbidden.
Yeah, heat guns are used very often, actually. Yeah, because
you have to be careful that you're not melting connectors. Connectors are melt. So we use on tape to shield the heat from the connectors. Yeah, heat guns are very useful.
Yeah, if you have to take off like an entire IC, you can't like solder all the pins at once, so you need a heat gun. Yeah. Also, just a note, we will be putting this slideshow or a link to it on Confluence and hopefully upload the recordings. So, another question? Well, I think that was a great explanation. It's really cool. And unfortunately, we can't host hardware tutorial this term, but a lot of this is reflected in the tutorial. So, yeah. But this is great.
All right.
Cool. Okay, well, if you guys have any other questions or comments, feel free to like give us recommendations or like suggestions if you guys are ever unclear or feel like we can improve in these knowledge shares. I'm not sure if we'll send out another Google form. So if you guys do have comments, just like Slack them or something.
Yeah.
Yeah.
Great.
Yeah, cool. Okay, well, thank you, Micah. Thanks, everyone. I think we're good. And we'll upload after it. Also, next week, I think we're talking about ASC and FSGP and WSC regs, which is really cool. Okay, so you guys should definitely show up. It's a lot of fun.
The regs aren't that interesting. The races are.
They're like, I meant the testing and like the like actual competition. That is cool. The regs are informative.